Now recording, so don't say anything too bad. So yeah, feed-forward layer. The normal feed-forward layer is like an example is just housing prices. So the way you like model this is you have a bunch of scalar values. Let's say this is like the number of rooms. I don't know what's some other stuff. Number.
Mass, square footage.
Yeah, square foot. Square foot. Number of floors, and so on. So you have all these variables that basically you have this data. In this case, it would be a house, and what you do with this data is you pass it through what's called a feed-forward layer, and what this looks like is you have a weight connecting all of these inputs. So these scalar inputs, and this would be say W1, W2, W3, W4, and W5. And you're going to get some output value z, which is just a linear combination of all these, and then you throw nonlinearity on top. So z is equal to W1 times the number of rooms. Maybe that is, we'll call this x1, x2, x3, x4, x5. So what's up? So z would be equal to x1 w1 plus x2 w2 plus so on. So that's how you get z, and then you usually pass this through a nonlinearity, which we'll call a is equal to some nonlinearity of z. That may be a sigmoid, but it's not going to be a sigmoid, it's going to be a ReLU. So you usually send this through a ReLU. So you have this linear combination, just a matrix multiplication, and a dot product in this case because it's just one node. And it's just a combination of all these features. And then you send that through a nonlinearity, which looks like this, just to give it some nonlinearity-ness. And then you do this multiple times. So you can think of this second node here. So this will be Z1, Z2, Z3. So each of these Z values is another linear combination using different weights of all the inputs. You can draw this in blue. So this would be Z2. And Z2 is this would be W1, W2, and so on. So Z2 is just another linear combination. Maybe I'll call this something else. Maybe this is like H1, H2. So it's just a different set of weights that you add up. So this would be X1, H1 plus X2, H2, and so on. So now you have this second feature, which is a different linear combination of all the original features. And you just have a bunch of these. And this may look familiar. All it is a matrix multiplication. So all you're doing is if you have some x, which is a d-dimensional vector, so you have some vector with d things in it. So maybe you have 4 different things about your house, then it's a 4-dimensional vector. And you just multiply this by a matrix. So it'll be x times some matrix, which is d by d. And each of these is, this would be like Z1. So it's just a bunch of, it's just a matrix multiplication. And then you send that through a nonlinearity. And a feed-forward network does this multiple times. You just do this over and over again, and you learn the weights specifically. You've probably seen the diagrams where you have like the nodes here, and this would be like x1, x2, x3, x4. And then you have some more nodes here, and you connect them all. And then you have some more nodes, and it's fully connected. And then you have a last node, maybe. And then this is your prediction, y. And what you do with this prediction can be whatever. Maybe in this case, we're trying to classify the house. Do I want to buy it or not? Then your output y, this would be y hat is your prediction. And then you just do normal logistic regression on that. So all it is matrix multiplication here, here, here. You pass that through a nonlinearity, and then that gives you your output. But this only works for vectors, and that's kind of the problem. I guess that's a really quick overview of how feed-forward networks kind of work. Does that kind of make sense? Okay, cool. So that's feed-forward. Now, like I said, this only works with a single vector, but with text, the way you encode text is you have multiple vectors. So you have a vector represent each word. So I like cats. We're doing this again. You got to correct me this time. I like cats, yeah. Yeah. So in this case, our...
The true statement.
It is true statement. So in this case, our vocabulary would be, say, I like cats and dogs, but dogs isn't in here. And then you have this lookup table. which is just a matrix multiplication. And each of these, so this lookup table will be of size, say, v by d. So v is equal to 4 in this case. We have 4 different words in our vocabulary, and d is equal to whatever dimensionality it is. You just make this really large so that you have this vector in some high dimensional space that you can work with. So this vector here would represent the word I. This would represent the word like. This would be cats. We'll make this dogs. And this is cats. So you have a vector representing each word in your vocabulary. So our sequence I like cats can be represented as 3 vectors. So this would be 3 by d, and you just stack these together, and this would be I, this would be like, this would be cats. And you can think of this, you can expand this to any size of v. So in the case of Bert, I think it's like 10,000 or something like that, but think of all the words in the English vocabulary, and you have a unique vector for each one. And if you have enough vectors, you can do that no problem at all.
And so the way that multiplication works is you just have some sort of mapping between like an actual word and a one-hot label, and so you just use it like a one-hot vector to like get the vector you want.
So if we like an easy way to do this is just a one-hot vector. So the word I would be represented as 1 0 0 0, and then the word, and you just multiply that with this big lookup matrix, and you would get this first vector, and then the word like would be 0 1 0 0, and you just do the multiplication, you get this, and that allows it to be continuous, so you can differentiate it. Now, to deal with this, we use an RNN or an LSTM. I'm just going to kind of show it at a basic level because LSTMs are kind of bad. So
yeah, they suck.
What you do is you have your first vector here, and you're going to throw this through an RNN cell, RNN. And you're also going to pass in this hidden state here, H. And both of these, we'll say they're the same dimensionality. So their vectors are the same dimensionality. And in your RNN, you pass both of these through, and you get some output, which will be the next word prediction. So this would be your prediction like. And this is also D. And then you pass this through the same RNN cell, and the hidden state is passed. So this outputs 2 things. It outputs the prediction, but it also outputs the next hidden state. So maybe this is H1. This is H0, H1. So H0 can start with all zeros, and this is just your vector representing I. You do something with it. Maybe you add them together. So for example, we can have I multiplied by a matrix W. So this would result in something. And then you add this to maybe H multiplied by another weight matrix, and maybe that's your output. It's very arbitrary, but and also we don't really want to go into LSTMs because they suck. But yeah, you're just doing some combination of this hidden state, which represents your past that you've seen, and the new word. So this vector here should represent the word I in some case, in some way or another. And then you pass this through you pass this through the RNN cell again. So you're actually passing this through the same thing. So this is just the same weights. And you pass in the word like. So now, so it already has knowledge of what was in the past, which is in H1. That should be I. And then it sees like, and it says, okay, I'm going to predict the word cat now. And maybe and it continues that. So then it'll output another hidden state here, H2, which should represent the word I, and then the word like. And you just keep on stacking this hidden state with the previous words it saw before, and it keeps predicting the next word. So it's just a next word predictor, that's all it's doing. That's all the RNN's doing, and you just update these weights. And to train this thing, you basically give it the whole entire sequence. It'll output its prediction for each part of the sequence, and then you just do normal cross-entropy on that. There are a lot of problems with this. Since you have to go all the way to the end of the sequence, the gradients vanish as you differentiate backward into the sequence. So you start from the end, and then you differentiate to the beginning of the sequence, to the word I. And as you do that, the gradients, they vanish or they explode. The exploding or vanishing gradient problem, which y'all have probably heard of, get really big or really small for the computer to handle.
And think about an RNN as like one network and you're constantly passing stuff through it.
Yeah.
And so it's called backpropagation through time. So when you keep backpropagating through a sequence like that, and you keep multiplying these matrices like that together, the chances of those gradients vanishing is really high. And LSTMs are like, they add a couple of fancy gating things that make it a little bit better, but it's still not great. Also, training's not parallelizable because you have to rely on that hidden state.
Yeah.
So that's another reason they suck.
What does that mean as a practical matter? That the prediction starts to fail as the sentence gets longer?
It doesn't
It
learn
doesn't do
well.
long sequences.
But yeah, it doesn't learn well. Like it as you increase the sequence length, it like the grade. Yeah, it just dies pretty much, the gradients.
Like what you were saying, you just drop it after a certain number of terms and start dropping the oldest term.
It basically does that because
Those terms just vanish.
as you go to a really long sequence length, since you keep to go backwards, you have to multiply by a bunch of matrices because you have to compute the gradient, and you have to compute the gradient over and over and over again. So it's just a bunch of matrix multiplications, and as you do that, you're probably not going to converge on a value. You're going to blow up, or it's going to vanish. And an LSTM kind of helps with that, but it's still not very good.
If you think about it, like if you're multiplying a matrix, right, and if you think about like if you would take the norm of that matrix and it's less than 1, your gradient's probably going to vanish, and if it's more than 1, they might explode. Right? If that's like a linear algebra perspective, maybe that helps. But
So is it not too familiar with the math of it yet, but like so kind of like a disk drive where it like reads and writes over and over, but eventually the quality of the old stuff gets diminished as time goes on.
Yeah, exactly.
It just dies eventually, just
Yeah.
from too many reads and writes, basically, or like inputs and outputs.
That's one
Well,
way to think about it.
you can think of it like you have this high dimensional space, and you can only store so much information in there. And as you continue to write to that, you have to get rid of old information. But also during training, so that's just during, but also during training, the gradients to update the first, like whenever you differentiate a function chain rule, you have to
Go all the way
you
back.
have to go all the way backwards. And whenever you go all the way to the end, you're probably gonna get a vanishing or exploding gradient, which the computer can't handle.
Okay.
And then you run into issues, which are not fun. An LSTM just does some special things to try to fix that, but doesn't do a very good job.
So what are
still.
the like use cases for this in particular?
I mean, nowadays, stocks, maybe. I think that's the only
There's,
thing
like,
it's really
very
used for.
limited use cases. You can still find some things there.
I think
people
stocks.
like in physics, they like RNNs.
Oh, right, because
For
it's a
some reasons.
you can continuously
Yeah.
update it.
Because you can continuously update.
Yeah.
but
There's not a
in
lot.
general, it's niche now, I would say.
The
In
transformer
language,
took
you
it
don't
over.
see it at all.
Yeah.
Like in language tasks, which I think are the big things like right now,
I
like
don't see it anymore.
you won't see it.
Yeah, so this was, before transformers, this was how you modeled any sequence text. You would give it a word, and then it would output the next word, you give it the next word, it outputs the next word, and so on. Now we have transformer models to do that, so we don't need this. And transformer models are a lot stable, which is what we're going to talk about next. So yeah, RNNs, not very good. So transformers, attention is all you need. There's a lot here. So the main part of this is attention. They have it in a bunch of places. They have it here, here, and here. And there's actually 3 different types of attention. This is multi-head attention, this is cross attention, and this is masked multi-head attention. And they're all basically the same thing, except there's a few differences here. But let's just go over attention. So the idea for this is you have a sequence, and you're trying to, in this case, they were trying to do translation tasks. So you want to translate, say, I like cats. What's the Spanish one?
Me gusta gatos.
Me gusta, I think it's actually Gustan or Gustan.
No.
Yeah,
Gustan, yes.
Okay, well,
Yeah,
what kind of Mexican are you, man?
I thought
Doesn't matter.
Isn't the end though about the subject saying?
Is whatever.
Specifically, me
Yeah,
gusta.
it's just
Me gustan
me
los
gusta.
gatos.
Is it Gusta?
Yeah,
Yeah.
it's just
Oh,
Gusta.
you're right.
You put los in between
Yeah,
gusta and gatos, but
because it.
We can do that.
Gusta is one of those
Gustan
like,
los
real
gatos?
goofy words
Yeah.
where it's like retroactively like. There ain't many of those. In
Makes it
Spanish.
difficult. Well, we're going to use that. So the goal is to translate from here, to here. And you want to train something that does this translation, and that was what they made this for. Hey, stop that.
So just to be clear, when RNNs before transformers were a thing, they used RNNs to do language translation. So you feed in like me gusta, dos gatos, sure, and it would output like I like cats, you know, and you keep kind of how it worked. I don't know if he's gonna do it right now, but how it worked is you would feed in like each word into the R. You'd feed in the word, and then the RNN would, you know, you feed in again in the next hidden state, and you keep feeding in the whole sequence. That's like whatever in English or Spanish, and then it would translate it after you fed in the entire sequence. It would translate it to English or whatever translation you're doing. As you can imagine, this is really slow, and like they said, it only works for really short stuff, because otherwise you're going to be feeding back into your RNN like a billion times, and it's going to have the vanishing or exploding gradient problem. And also keep in mind for the vanishing and exploding gradients that you're only going to have that problem during training. Like inference, you're not going to be learning the weights at all. So you're not going to, when you backpropagate, you only do that during training. So when we're talking about like vanishing, exploding gradients, we're referring to during training, your model will basically just die on you. And then you'll have to like restart your model from a checkpoint, and then
training is just unstable at that point.
It's very unstable. Yeah, exactly.
So the weights are in the hidden states?
Well, so the RNN, so it's a recursive neural network. So remember when we were talking about the feed forward network, you have those weights, right? You can think of it as the same idea. You're trying to learn those weights. So you back propagate through the RNN and you learn those weights, right? So when you're learning those weights, you have to update the gradients. And if you have if you feed back through the recursive neural network too many times, it's like you're compounding. So like a good example is like, you know, when you have like a value of 0.5, right? And you multiply, or you like take an exponent like 0.5 to like the 100th, right? That's going to go to 0. It's going to go down to 0. It's basically going to be 0. So you can think of the same thing happening here. If you feed the same thing back into the recurrent neural network many, many times, it's just going to go to 0. Or if it's really big, it's just going to go to infinity. So that's where the problem comes from. LSTMs use like a lot of like switches and gates to try to get rid of those problems, but it's not really good. And that's why like the translation task, that's why it's solely done by transformers now.
That's why all the text is. So the hidden state would be like x, so your input at whatever, or I guess this would be x sub I, times some matrix. This is just like a very basic one, but it would be like a feed forward layer for x, and then you add that or combine it somehow at the feed forward layer of the hidden state. And these are your learnable, your weight matrices, and then you throw out through some nonlinearity, and that's your new hidden state. There's more to it that you can do, but just like a very basic one looks like this. And then you have different weights to get your output, and something like this. But it takes in your inputs and your hidden state. And in this case, if we want to do this translation, it would be like you would take in the word I, and then like cats, and then you have this hidden state here. I think you actually use a different RNN for the output. So then you have this hidden state, which should encode the entire input sentence. And you can see where a problem may lie is you have this one vector, which encodes your entire sentence. And then you basically give this one vector to the output RNN, so this thing here, which is then going to decode that hidden state and give you your sentence.
And also to mention, the idea of like encoding your sentence, or like encoding this like or like, you know, you have I like cats, you want to encode like the meaning of it, right? The idea of encoding it and then decoding it into another language, it's going to be the exact same thing that we see in the transformer, where this is the encoding or the encoder and this is the decoder, and it's going to do a very similar thing where, you know, like
except not bad,
yeah. But it will encode your sentence as some internal state that's probably not human readable, but we'll try to, you know, say like, oh, this is kind of what you can think of it as. But it's the same idea. So you encode it, and then this hidden state is like kind of what you'll be passing through into here, right?
This one.
And then when you decode it, it's going to be what's happening over here. So you'll see that like how they're very similar in a lot of ways once we start going through the transformer.
We'll get to how it does this encoding decoding. First, we need to look at attention, because that's the main basis for this. So attention is given a sequence. I want to transform it somehow and make relationships between all the parts of the sequence. So this is the heavy lifter here. So in our case, we're just going to have 3 by 3. So I like cuts, and this can be any sequence. Any sequence that's n by d. In this case, n is equal to 3, d is equal to maybe 5, 1, 2. And then what you do is you first compute 3 matrices. So these matrices are just going to be a linear. It's going to be a matrix multiplication. So these are called your queries, and the way you get the queries is so we'll call this x here. This will be x. X is our input, and queries is just x multiplied by wq. So this is just some linear transformation. This is linear. It's not. You don't have a nonlinearity after it. Some linear transformation of the inputs, and this matrix wq will be a d by d matrix. That is really bad. I don't like that R. D by d matrix. So basically for each vector, you're just transforming it. This doesn't do any relationships between the vectors. This is just transforming the word I into something, the word like into something, and the word cats into something. So that's just WQ. This is just some transformation of every vector. Then you do the same for the keys. The keys are equal to x times WK. And WK is just a d by d matrix, and you do the same for the values, where V is also a d by d matrix. So you have 3 of these matrices now, and they're just different representations of this data. So it looks like that. And yeah, those weight matrices are learned. So the way what you do now is you multiply the keys or the queries by the keys. So this is QK transpose, and you get this matrix here, which is n by n. So yeah, QK transpose, and I think your keys are on this side. I always get them mixed up. It doesn't matter. Your keys are on the left, your queries on the bottom, and I'm gonna erase this so I have some space. But each of these like parts represent a certain or it represents a certain similarity score, basically. That's a good way of thinking about it. So you do the queries multiplied by the keys, and this first one represents Q1, K1. So you have a vector Q, and maybe your Q vector is I. It's a representation of I, and your first K vector is also a representation of I. So this Q1, K1 is a relationship between I and I, which is going to be pretty high. I'll just write out a few more. So this will be Q2, K2, and this will be Q3, K3. So this is like, this is cats, like cats. And this would be Q1, K2, and Q1, K3, and this is Q2, K3. And then you have this upper triangular, which we'll get to in a sec. But you can think of this first part here as being how does the word I want to send information to the word I. So that's kind of weird because there's only I in the sequence at this point. So it's just how does I relate to I, and it's going to have a high similarity score. I guess we can kind of have an example over here of what the similarity scores may be. So maybe this is like 0. This would be 1. So 100% relationship. If you take the dot product between the two, maybe you get 100%. So that means that they're the same. They're the same vector. Now, in the second case, which is more interesting because now you have information from the word like. Like this first query 1 times K2 is basically the word like sending information to the word I, and it does that through similarity score. How does the word like and the word I, how do those vectors, or how similar are those vectors? And maybe you're going to get, say, 0.3. They're somewhat similar, maybe not too similar. Maybe the word like doesn't need to send information to the word I. I guess you can kind of think of this as like what the third part I think is more intuitive, but the word like doesn't really need to send information to the word I. It's kind of arbitrary. And then how does the word like compare to the word like? Maybe 0.7. And then the third case, which I think is more intuitive, cats may have to send cats needs to send information to the word like maybe it sends information. So the word cats, this vector, needs to send information to the word like, so that the word like knows what is being liked. So it'll have a high score, maybe. And this is all arbitrary. It's just an example. And then the word cats and the similarity score between cats and I, maybe that's pretty low. You don't really, the similarity doesn't really mean much. And then the word cats and cats, maybe since they're basically the same, you have a high score for that. So maybe it's 0.3, 0.4, 0.6. Yeah. So you basically construct this similarity matrix, which is how does this, the key, send information to the query. And you do this through similarity score. And yeah, you're constructing this similarity matrix, basically. This top part here basically is sending information backward in time, but which you do mask, but we'll get to that later. For now, just this lower triangle is important because it's how do you send information to other tokens. So this would be, how does I send information to the word I? How does like send information to the word I? How does like send information to the word like, and so on. So you have this similarity matrix. It's a routing of information. How are words sending information to other words in the future? These words send information to the future words. And then you take the softmax to regularize this. So this first vector here, I already regularized them, but yeah, you just make them add up to 1. So that you have a distribution. So you can kind of look at this as, like this would be your first vector here. Your second vector would look something like this. Your third vector would look something like this. And you basically construct this distribution, which tells you how much information you're going to be routing. So this basically says how much of the word cats is going to make up the final vector. So you take the softmax, and then you finally multiply by the values. So multiplying by the values, let's go here. So your first output is going to be the first value times qk1. So q1, k1. And what this is representing is how much of the word I do I want to be in my output. So you're going to have 100% because we don't have these values here. So this will basically just be another representation of the word I. It's just taking that part of the distribution. So your second, so V1 is basically your representation of I, V2 is your representation for like, and V3 is for cats, just like the query keys and values. Now V1, or O2, wants a little bit of I, but a lot of cats because it's still a representation of the word cats. So this will be Q1, K2. And this is just weighing the first vector. So weighing how much of the word like do I want in my final output. And V2 is saying how much of the word like, or how much of the word like do I want in my output. So this would be Q2, K2. And then you do the same for O3, which is saying I want a little bit of the word I want a good amount of the word like, and I want a lot of the word cats because this is the word cats. So this would just be V1, Q1, K3, plus so on. So now you have this output representation, O1, O2, and O3. And to kind of put this all in a formula, you have your output is equal to queries softmax of the queries, keys, transpose, times your values, times values, dot product values, big dot. So yeah, that's attention. It's a routing of information where one vector is basically sending information to another vector through similarity, and your output vectors are a linear combination of all other vectors. And these similarity scores tell you how your output vector, your output representation for a word is going to look. So this one is going to be a linear combination of the word like and I. This one's going to be a linear combination of I like and cats, and this one's just going to be a linear combination of the word I. These can be zeros. So all you're doing is routing information. Does that hope that makes sense, but that's all attention is doing. It's just routing information. We have a new set of words, O1, O2, and O3, where the word I is a linear combination of the 3 words, where it was just the word I with 1. The word like is a linear combination of the first 2 words, and the word cats is a linear combination of the first 3 words. So it's routing information from the past to the future. Does that make sense to everyone? If not, please let me know.
So the bigger your matrices, the closer these values get to 0?
Yes, because you have to normalize it to a distribution. So you normalize it along this here. So you have this distribution, but maybe if you look at the attention maps, you usually have a few words that send a lot of information, and then the other words don't send much information. Because if you think about a sentence, like in this case, it needs to know what is being liked, or who is doing the liking. So the word I is doing the liking. So it would send a lot of information. But if you have the word like and, then that's probably not very useful. And maybe it's the word the. The word the is pretty useless, and is kind of useful.
So just reiterate again how it's calculating the usefulness of each word.
Kind of like every vector wants information from the other vectors. Mm-hmm. So kind of how useful is this information for one of the vectors. So the word like is like I want some information from all the other vectors, mm-hmm. and then it calculates the usefulness of those other vectors. That's how you can kind of think about it.
Yeah.
And
if you're a fan of graphs, you can think about it like
fully connected graph. So in this case, we would have I like cats, and I guess is an interesting triangle. That's our graph. But if we have 5, we can draw a pentagram.
Oh my god.
As you can imagine, I and cats probably wouldn't be as, similar to each other than like I and cats, would be to I and cats. So you can imagine this. That's why we have this.
It's not the similarity of words. It's a similarity of the vectors of the words. Right. It's how do I want to send information. It's not how similar are these words. It's how do I want to send information, and you're doing that through similarity of the vectors. But that's different than how similar are these words, because that could be like, oh, this is a verb and this is a verb.
Right. Yeah. Or like, how do the words relate to each other in this sentence?
So let's say through the English dictionary, would the values have to be predetermined of each word, or would that be done within the matrices, like
the vectors?
Yeah.
No, so those are all all of these are computed on the fly through matrix multiplication. So Q, K, and V are all computed through just a matrix multiplication, one feed forward layer. So your values, you don't actually need these here. You don't actually need the values. You can just use your original inputs. So the word I, it's a lot easier to think about it if you don't have your values here. So in this case, this would be X1. So your new output is just X1.
Okay.
And then in this case, this is X1 and X2. So it's a little bit of I, 0.3 of I, and 0.7 of the word like. And that's your new representation of like, which now has information of the word I. The values just transform it because why not? So throw some more parameters at this thing. It'll do a little bit better. So if that all makes sense. Cool. So I mentioned this masking part here. If we do add values here, let's say 0.3, 0.3, and 0.4. So if we do have values here, then this is basically information flowing into the future. Let's say whenever I'm generating a sequence, I only know of the word I. Let's say I start off with the word I. Then I don't know of the word like in cats, but I know, during training, I do know that. But during inference, if I just have the word I, then I need to predict the word like, and then I need to predict the word cats. So you have this mask here so that the words don't look ahead in the future. So the word I here, whenever you have this mask here, so that it can't look in the future. So this part here cannot attend to the word like and cannot attend to the word cats. And by attend, that's just the word that's used. By attend, I mean it can't do anything with that. It can't send information to there. So when you're training, you know the sequence. You know we have I like cats. But during inference, you only know the word I, so you can't actually do this. And this is a little trick you do where you mask out the upper triangle so that the words cannot send information into the future, and you can train in parallel, which we'll show later. But this is what's called masked multi-head attention, or masked attention, not multi-head, where you mask out the upper triangle so that words cannot send information into the future, unless that token is known. So if you look at the 1x1 case, so this constructs an n-by-n matrix, and if you look at the 1x1 case here, then the word I can only send information to the word I. But if you had your entire context, then the word I can send information into the future, and you don't want that. So you mask the upper triangle so that you can do this in parallel. And if you look at the 2x2 case here, then you have the word I, you have the word like. I can send information to the word like. Here I can send information to the word like, but that's after I has already been generated. But like cannot, like can send information into the future. So like can send information to the word like. I can send information to the word, I think I'm getting this mixed up. Basically you mask this upper triangle so that it can't look in the future. And at the end, later we can show why this is helpful, because you can parallelize this if you do this upper triangle masking.
Kind of how you can think about it is like if you have when you're doing training, you're gonna have like a sentence, like you're gonna be feeding it sequences, right? So it can learn from those sequences. If you feed it a sequence and you're trying to like generate new text, you don't want it to know what the text already is, it's that for it to because then it will be like, oh yeah, I already know what this is. I know what's in the future, so I'll just like generate that, So it would already know what's going on, and you don't want it to do that. You want it to be able to generate this, the text. So that's why you were going to mask out that top right matrix, or the top right triangle, so you don't have like I knowing what's coming next, or like knowing that cats is the next word.
So if we look at this sequence here, this would be I, this would be like. So during inference, this is what you're going to see. During inference, this will be your first state. It'll just be the word I. How does I attend to the word I? It's just a 1x1, doesn't matter. Then this is your next hidden state. This is your next matrix, your attention matrix, once you have the word like and I. So that's what this would look like. This would be I, this would be like. And so now this can send, so you mask out this part here so that you can do this in parallel. So during inference, you don't know that I doesn't know it needs to send information to the word like until you have the word like there, which is why you do that masking there. This has all three words in here, and we mask the entire upper triangle. We can show later exactly why they do this with the loss functions to kind of show that, but this is the mask part where you just mask the upper triangle so that tokens cannot attend into the future. They can't look into the future and say, oh, I already know what's going to happen, because they won't during inference. So that's the idea of that.
Just keep in mind, in our attention mechanism, not all of them are going to be masked. You'll see that some of them are just like regular multi-head attention. Some of them are, or we have that one where it's masked multi-head attention. Kind of idea is like in your encoder, you already know what the sequence is going to be like. So for translation, for example, if you're translating the sequence I like cats, you already know the three words, so you don't need to mask it, because it should know what's coming next. It has all the context. But when you're actually trying to figure out what's gonna be the output sequence or the output embedding, you don't know what's gonna come next, so you don't want it to actually you don't want it to know that stuff.
Yeah. So
when you're doing inference, you just want to have it trained in a way to where it'll actually be useful for inference.
Right.
That's really what this is.
yeah. So if you look here, you have normal multi-head attention. Normal multi-head attention allows you to construct this full matrix here, so you don't mask out this top part here. Because you already know I like cats. You already know that, and you're trying to translate to the Spanish form. So you don't have to mask out this part here, because the tokens can look into the future, and it doesn't matter, because you basically know all the time there. But for the output sequence, since you generate one token at a time, you have to mask the upper triangle so it can't look ahead, and you do that during training. Now, let's do cross attention first, and then we'll do multi-head attention, because right now we just have attention. So cross attention is basically the same idea, except it's if you have two different forms of this matrix, and there's multiple ways of doing cross attention. I will show I think I should show the diffusion case, because I think that's the best one. where you have the
But the
queries.
queries and the keys are different,
Yeah,
right?
yeah.
Yeah.
I think that's the best case so far. Yeah. So there's a lot of different ways you can do this, but the basic idea is we have some sequence here. So we have this output sequence. We have some sequence, and we also have another sequence, and we want to combine them somehow. And a good way of doing that is through cross attention. So let's say we have our sequence I like cats, and then we have our sequence. I'm going to shorten it here. Me gusta gatos. During generation, we can add los. So you have these two sequences here. Maybe this is X, this is Y. Now you want to combine this information somehow. Now with normal attention, you would compute the queries, the keys, and the values from X. From X. So you would compute your query keys and values from X. Actually, no. Let me add the fourth word because that'll make it more interesting. Gustan los gatos. So yeah, this is a big problem because they're different sequence length. And remember, your queries times keys is an n by n matrix. But let's say we did this, where we have X be the queries, we have Y be, well, let's have this be the queries and the keys, and let's have this be the values. Then we get an n by n matrix, and our values is, let's call this n is equal to 3, n is equal to 3, and this is m is equal to 4. So this would be an m by d. Now there's a problem because you can't multiply an n by n matrix with an m by d matrix, so you can't combine the information this way. What you can do though, so you kind of have to mess with this equation a little bit. What you can do is you can make X be the queries. X be the queries, X be the values, and I'll draw this in blue. Have the input sequence be the keys. So our matrix here. Is that right? I think no, it's the other way around. So you would have the this be the keys and the values. Was it? Do you remember what order it was? I think it was.
You're multiplying along the d dimension, so it's going to be the keys
one
and the
sec.
queries, or I mean, X will be the
D
keys and
by
the
M.
values, and then
Yeah, and then
Y
Yeah,
will be
X
the
would be the
keys.
keys and values, right?
yeah.
Yeah, and that would be the queries. Okay. Always forget the order of that. So yeah, so you can mess with this in such a way where you do get an output that you want. So in this case, we can have Y be the queries, X be the keys, and the values, and then you get an M by N, or N by M matrix, where this part represents the input sequence X. So this would be like I like cats. This would be your input sequence X, and then X here, and then this would be me gustan los gatos, and that would be your M matrix, your Y, and basically you just have this routing of information, and this isn't masked. So that would be 4 by 3. So you basically have this attention matrix that is constructed that allows these tokens to send information from the English sequence to the Spanish sequence. That's how you can think of it. The English sequence is sending information to the Spanish sequence you want to generate. Maybe this continues on. In this case, we already have the full sequence, but let's say we don't have gatos here. Maybe we have just me gustan los, and you want to predict the word gatos. Then the input sequence I like cats is sending information to the sequence to inform it, hey, you need to generate the word cats. So that's what it's kind of doing. Arbitrary in how it actually does that, but because it'll learn that. But that's what you can kind of think of it as doing that. So this would be an N by M matrix, and then your values will be this is N by M, so this would be M by D, and then you multiply along this M dimension here. this is actually your values are actually your Spanish. No, yeah, I was right. Yeah, it was like that. I always forget the order, but yeah, your values, which are your Spanish sequence, which you're trying to decode, would be multiplied by your attention sequence, which just is a new linear combination of your tokens. So yeah, all you're doing is routing information from the Spanish sequence or from the English sequence to the Spanish sequence, and it's just informing the Spanish sequence what to do next.
Okay.
And it's called cross attention.
Sorry.
Yeah.
For cross attention, just a quickly note for this whole thing we're doing. The main reason that we do like these different routings of things is just to make it like work the exact same way as regular attention does, right? So you know how when we were doing it earlier, we had like the 3x3, so it was like really nice and easy because it was all just like a square matrix, right? Well, if you were trying to like multiply in the same way, but you didn't have the same sequence lengths, then it would just die. It wouldn't work because the the dimensions wouldn't be the same, right? So we're routing the we're putting the information in different like the keys, queries, and values differently from before, just so at the end we have that n by d matrix that we had, when we did regular attention, and it's actually going to be a very similar thing when we do the cross attention in the transformer. When we do the decoding, you see we have the information from the encoder routing into the cross attention. It's gonna be the same idea. We just want to mash everything together and put everything together so it works good. So that's kind of why we're doing the cross attention here.
It may seem like a dumb way to condition, but
And it is, but it works.
Machine learning.
So yeah, all you're doing is you're
If
constructing.
something works empirically, that's good enough.
All you're doing is constructing this big matrix, which is how am I sending information from the English sequence, the input sequence I want to translate to the output sequence, the sequence I'm trying to decode, and that's all it's doing. And you do that in a way where the dimensionality looks good. But the softmax attention matrix is what really matters. It's how are how are you sending this information?
The whole attending analogy kind of falls apart here. But
It does.
Just ignore that.
Yeah,
It works in practice. I mean,
yeah.
Just because like the
yeah.
sequent links aren't the same size?
Yeah,
But, like,
they
the
won't
whole
be.
idea of attention, right, is like every word attends to another word, but if they're different sequences, that doesn't really, like, that analogy doesn't work.
I guess it kind of does. So like in this case, the word I
I
maybe
guess
needs
here
to
it's okay,
inform
but,
some
like,
of the
way
words.
they use it in stable diffusion, where you
Oh, no.
that doesn't work.
Interesting.
We don't need to talk about stable
We'll
diffusion.
talk about it
That's a
next
whole
week,
new
right?
thing.
You'll see what we do.
So with machine learning, you'll see that often what they do, like people who are actually like developing this stuff, they'll literally just take random models from other places, just shove them into random things, and then pray to God that they work. And then usually they do. And they're like, wow, this is so cool. Like if you look at the stable diffusion paper, which we said
I think
we're not
it's
going to
more
talk
accurate
about.
to say if they wrote a paper about it.
Then it-
Yeah, they wrote a paper about it.
There's definitely a lot more things they
Like
tried.
the stable diffusion paper is literally like an amalgamation of like 7 different things. They just like literally shove a ton of crap together, and for some reason it's like the best thing for generating images now, and it's literally amazing at it. So yeah. If you read that paper, they have a really good like image of it, and you'll see they just like have like they have like self attention layers and cross attention layers.
that's
They
how they
put it
do
into like a
cross-attention.
convolutional neural network, and then it's like, oh yeah, this is we just put these things together, and wow, it's learning really well. Wow.
If you just
And
add
they
all
use
the
an auto
embeddings.
encoder.
Yeah, and they use an audio encoder too. It's like it's yeah.
We'll probably go over that paper, the stable diffusion one.
We will eventually.
Yeah.
And then you'll see what we mean by they're just shoving a lot of stuff together.
So yeah, it's a fun paper, but this is this is basically you construct this full matrix for 2 sequences for this cross attention here, and for this attention here. So this attention here is the cross attention. This attention here is your input sequence only, which you have the whole thing. That's just normal attention. And then masked attention is you mask the upper right triangle so it can't look at the future. So that's attention. But there's a multicat version, and it's very simple. So let's say we have our sequence. Again, this is the last time I'm drawing this sequence for an attention matrix, but
We really like cats.
I do. I could write that up more. But we have n is equal to 3, and you compute your query keys values. Yeah, you get the drill. and your query keys and values will be an n by d matrix. Make this a little better, n by d, and your values will also be n by d. So multi-head attention, all you do is you split the d dimension into multiple parts. So in this case, it will be kind of hard to draw it. It'll look like this. It'll be like a thin part. Draw it like that. So this will be h by d divided by h by n. So what you do is you take this d dimension, which looks like this, and for each vector you just chop it into parts. And you chop it into h parts, and each of these are d divided by h. So you can think of this as kind of having multiple different spaces it can work in. Instead of it being a single vector, which you do the dot product with, you now have usually h is equal to 8. So now you have 8 different vectors which represent each word instead of one vector which represents each word. And that just, they do that, it works, and yeah, it just allows you to basically send information into different spaces as opposed to having one space where you have to do all the computation in. It gives it more representation power if you do that.
Do you
And
want to
all
show
you're
the
doing,
picture in the paper for it? Because they have a
Yeah.
really nice picture.
they do.
Yeah, so here's
Yeah.
the scaled up
Yeah.
model
Oh, yeah.
if you had attention. So you can see it's kind of like, you know, they have a lot of them, you know. They split everything up into many different, you know, linear layers, and then they just shove it into scaled dot product detection, which we talked about earlier, and then they just, you know, put it back. They basically split it up, do attention on the small parts, put it all back together, and then they're like, this is good, and they put it through another linear layer.
Yeah.
So yeah.
So this would be your n
One
by
of those
n.
things, it just works well.
You know?
Yeah.
You multiply this by the outputs, so your outputs will also be this. It'll be n by d divided by h by 8 by h. And then you merge these together, you just stack them together like you unmerged them. So then you get out an output, which is n by d, and then you throw this through another linear layer so it combines all the heads together. So now you have another output matrix WO, and that's this part here. So that's all it's doing. So you don't actually do attention with the full vectors, you do them with the split up ones. And it just,
also allows you to parallelize, so good for GPU training.
yeah. So that's multi-head attention. Yeah, that's all it does extra. Yeah, and here's the scaled dot product attention graph that they
You
have.
can see they don't really have a good explanation for it. So
Yeah, they just
Um,
have it there.
It just works.
And here's the formula. So yeah, queries, keys, transpose. You throw it through a softmax.
Oh, yeah, we didn't talk about the dimension term.
That's what I
That
needed.
is just something that's important for the gradient.
Yeah, for a gradient of the
Don't know
softmax.
that.
Just
It's not
scales
that
it.
important, but.
You guys mentioned for RNNs, like the gradients just like destroy themselves.
Yeah.
How does transformers prevent that?
Well,
Transformers work well.
we'll get, so
Yeah.
now that we have attention, we can get to how you actually train this thing, because attention is just one part, but yeah, you'll see it doesn't, because you, instead of sending it one word at a time, you send it the entire sequence at one time, and it doesn't blow up because you don't have a hidden state that you have to keep.
Oh,
If
okay.
you
And so-
think
so
about
it's
this,
really
this
helpful.
actually has no notion of like temporal
You
place.
you
Like,
do have a
yeah,
hidden
yeah.
state, but well,
Yeah.
you do have a hidden state, but it's one
You don't
hidden
have time
state.
information.
Yeah,
we,
it's
haven't,
different.
we haven't shown you how to add time information. Right now, this is like,
Yeah.
there's no hidden state. There is none of that's happening.
But we'll get
But you can
to
add that.
the hidden state. Yeah.
Yeah.
So yeah, let's go through now that attention is out of the way. Let's go through this piece by piece and put together the transformer.
kind of like a quick side note. So I didn't know this for a really long time, so this is why I'm mentioning it. But attention wasn't actually like made in this paper. Like it wasn't introduced
No.
by this
It
paper.
was used in RNNs.
And I thought for a really long time that attention was like from this paper. It was made like not very.
It was made by,
but-
I think,
It was like
attention.
a year before. It was used in
No,
GMT.
Yeah.
No, I think it was
GMT used it.
the scaled dot product attention. I'm pretty sure that was made by neurology
Yeah.
Oh, but I mean, so like
formula.
there was a paper that came out like a year and a half before this. It was also by Google. It was Google Translation, and that was using RNN.
No, before that, they had a paper.
Yeah.
It was
But that network used attention on the last layer.
it was
So basically, some people at Google were like, "Oh, why not just use attention for all the layers?" And that's how the transformation.
As you can see,
That's how it
the history of attention before this paper is like
Non-existent.
very hard to learn about. Like it existed, and we know it existed beforehand, but like trying to find information about where it came from is like it's actually impossible.
Google did it, according to them.
I swear to God that they hid all the information so they could like claim attention for their own. Like you look it up, like where did attention come from, and it will literally the only thing that comes up
Is
is
attention
references to
something.
this. So
Yeah.
just know that it's not from this, but good luck trying to find where it actually came from.
Yeah. So, on that note, yeah. So we'll go through this step by step. So the input embedding, you have two lookup tables. One lookup table is a Spanish table, and one lookup table is the English table. That's just your input embedding that allows you to get the d-dimensional vectors. Positional encoding. So positional encoding, I like to show like this. So you have to add positional information somehow. If you look at the attention mechanism, you can change around the tokens and you still get the same output. So if I were to have like, I, and cats, the representation for the word I is the same as if I had I like cats. The representation's the same because you don't have any positional information. Positional encodings add positional information to each token so they know where they are in the sequence. To do that, we can have sine waves of varying frequencies. Let me do this. So we'll have 3 waves. There we go. And let's say we have the word the sequence I like cats. So this would be I like cats, and this would be your dimensionality D. Which is equal to 3 in this case. D is equal to 3. And this is kind of like a high level of how you would do this. There's formulas for this using Euler. But what you do is you just sample this along you just sample this at specific intervals at the same interval. And you can do that a lot. And if you have enough sine waves, then you get unique frequencies, and this frequency always represents the first word in the sequence. This one always represents the second, and this one always represents the third. So all you're doing is sampling these sine waves, and since they repeat at some point, but if you sample them, if you have enough of them and you sample them uniformly, then you'll be fine. So all you're doing is sampling these sine waves, and each one represents a position. And now you have this vector, and you just add it to the vector I. So
it's really stupid.
This is your embedding.
It's really dumb.
This is your positional information. Yeah, and you just add
it.
them,
Yeah.
and
It's fun
it
talking
works.
information.
So now it has the positional information in there and the word information in there, and it figures out how to deal with that. Okay, so now let's look at the left side here. So on the left side we have move this over. We have the inputs, and then you add. What's up? We add the positional information, which is just from the sinusoidal embeddings, and then you throw this through multi-head attention. This is your queries, your keys, and your values. And you keep the skip connection here. So skip connection just allows the skip connection is kind of cool because it allows it to basically use residuals as opposed to using absolute information. So it changes the input information as opposed to reconstructing the output information from the input. So
if you want to think about why that's useful, it shows up everywhere, but
Yeah.
it's really just good for the gradients.
it is. Yeah. It's just good for the gradients. ResNet paper, if you're interested. You were talking about that earlier.
Yeah.
So we have that, and so you throw this through the multi-head attention. That gives you your new sequence, and then you do this add and normalization. So you add the residual. So that would be like this. You have your input x, and then your attention is equal to multi-head attention of x. And then you add these together and do the normalization. So maybe that's y. Y would be here. Would be equal to the normalization of x plus the multi-head attention of x.
Yeah.
Now,
Normalization is also also there for the gradients?
Everything's there for the
Yeah,
gradients.
everything's there.
Well, the normalization in this case basically prepares it for the next multi-head. Everything, all these parts here are basically preparing it for the next multi-head attention layer. There was a paper on that. So normalization, layer norm. What this does is we have our sequence here. We take each of these independently. So this would be our d-dimensional vectors. We take each of these independently. We look at the distribution. So this has some distribution of these values. It looks like this. And we move it to be a distribution with mean of 0 and variance 1. It's probably not going to be a normal distribution, actually. I take that back. It could be a normal distribution. The weights actually do end up being normal. But yeah, you basically shift it so that it has a mean of 0 and a variance of 1. And then you allow it to pick the mean and variance so it can update it. So you shift it, you force it to be a mean of 0 and a variance of 1. So you just divide by you subtract the mean and divide by the variance. And then you allow it to shift it wherever it wants. So you give it a couple parameters. Let's say we just have one token because it's on a token basis. It's not over the whole sequence. These parameters do not affect the sequence. It affects the token only. So if we have a token where d is equal to 3, then you give it a few parameters. You give it a mu for each of those and a sigma for each of those. And it basically says, okay, we're going to shift it so that the entire vector has a mean of 0 and a variance of 1, and then you can shift it by mu1, or you can shift it by mu1 and then spread it out by sigma 1. So it's just normalization. It's called layer norm in this case, but there's other normalizations like batch norm.
They're all essentially the same. They just usually will normalize along something different.
It's so you don't have values that are like 100 in here, so because then that'll break things. Now
it makes your training more stable.
Yeah.
That's usually what all these normalizations are good for.
Now we have the second part, which is feed forward. So feed forward layer, all you do is you take your token. So like I said, this is a token basis. You don't find any relationships through this. So this is D. You usually send this through some linear layer, feed forward. Maybe this would be X, this would be X W, this would be sigma XW. And then this output here will be sigma of, this would be sigma of XW, I guess that would be W1, W2. And that would be another layer, W1. So you just send this through a linear layer, and usually what you do is you have this dimensionality, you broadcast it to a 4 times larger dimensionality, and then it's like an inverse bottleneck. So inverse bottleneck, and it's just because like this feed forward is just here to prepare it for the next layer, for the next multi-head attention layer. And then you have this add and norm again, which is the same thing. And you stack these blocks. You stack n of these blocks, and you just stack them up, and you got a lot of parameters. And this will output a representation of the word I like cats, which will be your n by d matrix. This is your representation for I like cats, arbitrarily, maybe not, you don't actually know. But you have this is your hidden representation here. This matrix here, this is your hidden representation for your entire input sequence though. So you parallelize your entire input sequence. Remember, with RNN, we had to send each token at a time, and we only had a single vector for the input sequence representation. Now we have a vector for each word in the input sequence representation, so it's a lot more representation power. Then the output. So the output here would be your me gustan los gatos. You send that through the input embedding. You do the positional encoding. Then you do this masked multi-head attention. So that's your multi-head attention, but with the upper triangle masked, like this. And that allows you to parallelize this training. So this is just self-attention. Self-attention meaning it's attending to itself, as the name implies. And you do the add norm. And then this cross-attention, which is not doing attention to itself, where this is the query, this is the value, and this is the key here. yeah, so this is just cross attention like we showed. Then you do the add norm again, and then you do a feed forward layer, and you stack these up. Then whenever so your output will be your M by D matrix. So maybe this is me gustan los, and it needs to predict the word gatos. So when you're doing inference, what you will do is take this last token, throw it through a linear layer, take the softmax. So the linear layer basically takes this token here, which is of shape D, and broadcasts it to this massive vector here using a feed forward layer of shape V, where each of these values represents like a probability of, because you do a softmax, a probability of that word being next. So this would be gatos. One of these represents the word gatos. So if we have me gustan los gatos, maybe you have some other words, then it'll be every word that you know of, and that'll be in your that'll be the output prediction.
And on that output, so conventionally writing classification, usually you just take the max. But that doesn't work all that well in
Yeah,
practice.
it's pretty bad.
Yeah. If you guys ever use like autocorrect and you get like the repeating words,
That's why.
that's basically why. Right?
So you actually sample
can
from the
sample.
distribution.
Yeah. And if you sample, you'll usually get like better output because it's not going to get trapped in a loop.
Yeah.
Just scroll up.
So yeah, I mean that's the transformer architecture. Now I've mentioned parallelizing this thing. So what you do for the decoder is you give it the sequence. You give it the entire sequence. So you like with an RNN, you have to do it one word at a time. And during inference, you still have to generate it one word at a time. So you give it the entire input. It'll give you the entire hidden state. But for the output, you still have to generate that one word at a time because you don't know what the words are. So it would generate the word me, and then gustan, and then los, and then gatos, and whatever, so on. But during training, we don't need that. We can send the entire sequence through one time. And to do that, we do this masked part here, which we mentioned earlier. And if we had our input, this would be x here, n is equal to 3, this is d, then the only layer that actually matters is the masked multi-head attention if we want to try to parallelize this thing. And if you think about how you want to parallelize this, you want to construct this matrix such that the words do not look ahead. Because if they look ahead, then you run into issues. And that's why you have this mask here, so the word I cannot look into the future. And this will give you an output. Say the output 01 is equal to just, this would just be x1 times the attention value of that, which would just be 1. So, and you just bring this up the layers, and 01, your first word, will only be a combination of the first word itself. So everything in the past, which is nothing, it's just the word I. And you bring this up, and you send this through the linear layer, and you get your prediction for the next word. And since it's only a representation of the first word, since you mask the future, you can actually slap on the second part of the sequence, the word like. And if you mask this properly, this will only be a combination of the word I and like. So this will be x1, a1, plus x2, a2. I guess this would be 1, 1, 1, 2, 2, 2. So now you mask the future so that it doesn't look in the future, and O2 is only a representation of the past. So if we do this, then you have your transformer here. Your transformer takes in a sequence, which is of shape n by d, which is your entire sequence. This is your entire sequence, me gustan los gatos, and you send that through, and you get an output sequence that is of shape n by d as well. And each of these tokens here, you get an individual loss term, which represents the next token prediction because you masked all future tokens. If you didn't do the masking, then it looked into the future, and these are invalid. These losses are invalid. However, since you did mask the future, this loss, and the third loss, This loss here, you would want it to predict gustan. This loss here, it would be los. This would be gatos. And you can do this in one step. So you just throw this through the transformer one time, and since you mask the feature, you have the loss for every part of the sequence, as opposed to doing this one at a time and sending it through the transformer n times, where n is your sequence length. So yeah, that's why you do the masking. And like I mentioned, this is the only thing doing inter sequence communication, so you only need to mask this, not anything else. Yeah, so I think that is all for the transformer. Anything I'm missing I can think of? I don't think so. If y'all want, I can continue on with LoRA. Up to y'all. So if y'all are cool, I can start talking about LoRA, which should be quick. It's pretty easy.
Quick.
Yeah.
Even QLoRA is not bad.
QLoRA is pretty simple, but we probably
Might run out of time, though.
yeah. What time is it? Yeah, we'll go over LoRA real quick. So
if you guys want more pizza, go.
yeah, feel free.
Especially while we're like transitioning to papers, feel free to get more.
Let me find LoRA.
If you want to put the pizza over here,
The trash.
the trash pizza. Feel free to put it over here.
I feel like y'all always have so many boxes left over.
No, actually,
Feel-
last meeting we had.
Last meeting we
Yeah,
didn't
yeah,
have
we
any.
didn't have any. Yeah.
Today we will.
Yeah.
I'll try to,
Yeah, whittle it down a little bit. Yeah, I got
Unless you
you.
go crazy with them. Sorry, eat 2 boxes by yourself.
Thank you very much. Liam, you wanna? Thank you. Thank you so much.
Do I just not have LoRA in here?
You want LoRA?
He probably does.
Yeah, there's no way. I refuse.
Well, you read it a very long time ago, huh? There's Q, Laura. Wow.
Can't you just search for it?
I don't feel like it.
There's a search.
LoRA. We have QLoRA. We have InstaFlow. We have Wizard.
Wow, fake fan.
Wait, I'm a big fan of LoRA.
You
Don't.
got all the
You
Laura
got
variants.
LoRA in there. Not a
You got-
real LoRA
you got-
fan like me, bro.
Yeah, facts.
I have the LoRa paper as my background.
Wow.
I-
Yep.
Oh wait, I may not have the LoRa paper, but
Wow.
oh, let's go. Found it.
Okay, okay.
All right, I may not have the
I was
LoRa
worried.
paper as my background, but I have that picture. I have like a poster on my wall, and I'm like, hell yeah, check out that thing.
Just wake up in the morning.
I wake up,
You
and it is
wake
a good day when I see this.
I see
If I wake up and I don't see that, I'm in a bad mood.
Entire day, yeah,
Yeah.
I've seen it. It's not good.
No.
He needs
Like-
his Laura.
Pissed off. Like, god damn it. Didn't see LoRa. I actually didn't even really need to pull it up. But I do like seeing this.
He's gonna marry a girl named Laura.
Yeah.
So we can say
Oh,
hi
yeah.
every day.
Hi, Laura.
Alright.
Make all the memes. Yeah.
Anyways.
Yeah, so
That was funny though.
LoRA, so whenever you have this large language model, you need to you want to fine tune it somehow. And if you were to do the full fine tuning, you need to change all the parameters, which is first off, it's not very stable because you're taking these parameters and you're just changing them to a new task. It's kind of annoying to deal with that. But
And the data set you're fine tuning is usually a lot smaller.
yeah, So you usually
fine-tuning
start
the
with-
entire thing is
it's not a good idea. So and that's what was done before LoRa. But also, there were other methods, but basically that was what was done. But also it takes up a ton of memory. If you look at Atom, it takes up 3 times as much memory as there are weights. So that's a lot. If you have a 7 billion parameter model and you store those in 8-bit, then that's 21 gigabytes of memory, just storing the model and its moments. Sending the data through takes even more. However, we have LoRa on our side, so we don't need that. I was like, oh, okay. So What LoRA does is it works on linear layers specifically. So attention is just linear layers. That's all it is. Linear layers with some normalization. So if we look here, we have. I'll just show this. Yeah. So if we look over here,
I love that image.
this image is kind of hot. I gotta say.
God.
So
I
you
agree.
have your vector here. So this vector is a representation of some word. Maybe this is the word I. And you have your weight matrix here. So if you, in attention, remember we had a vector, we computed the queries, keys, and values, and we had 3 different weight matrices here, which were all D by D. D by D. So we had 3 matrices here, and the output matrix was actually D by D as well for the multi-head. So we had WO, which is also D by D. And we also had the feed forward layers after every normalization. So you had your feed forward layers, which were not D by D, but that's fine. You can this generalizes as well. But they were, say, D by D, and then D by D. That's stupid. D by K, and then K by D. But anyways, yeah, you have a lot of feed forward layers, and that's what makes up all of your entire transformer. So this is useful. Now, what we said before is you would usually take your weights. So you would take these weights, your pre-trained weights. So you train this on some massive data set like Llama or like GPT. You have this massive data set that you train it on, and then you need to fine tune
Basically
it.
The entire internet.
Yeah, the entire internet. You have this model that knows everything.
Plus, like, a couple book data sets.
Yeah, maybe a couple of leaked data sets as well.
Yeah.
Yeah. But that's what these weights represent. It represents this global knowledge. Now, we could just fine tune this. However, what they suggest is freezing that. So you freeze these weights, meaning that they don't update, but you still have to send the information through because this is what this is what your model was. So your initial H was equal to WX. Now, your new, what they propose is you put these low rank matrices here, which are the ones you're going to train. So let's say R is equal to 1. That's this matrix here. Then what you have is you have A, which is a D by 1 matrix, which is just a vector. And then you have B, which is go over here, is a, what is my pen size? Why is it 10? It's like thick, is a 1 by D matrix. So it's D by R and then R by D. And if you multiply A and B together, you get a D by D matrix. So AB, I don't care what sides you multiply them on. You get a D by D matrix. It's trivial what sides you multiply them on. Then you multiply along the R dimension, and then you get a D by D matrix. But you only store R by D data. You only store R times D memory. So if R is equal to 1, then you're not storing D squared values in your memory. You're only storing D in your memory. And the values you have to update. Remember how I talked about Atom and how you go from 7 billion parameters to 21 billion because you have to store the moments, the Atom moments. In this case, since you froze your original parameters, you won't go from 7 billion to 21 billion. You'll go from 7 billion to maybe 7.5 or something, probably even smaller, because you only optimize these parameters, and Atom will do this times 3. So it'll be R by D by 3, and that's the memory you store.
So the only
because of Atom.
gradients you're storing are going to be
Are the LoRa layers. So these are the ones you're optimizing. So you have this original, you can kind of think of it like we have this original knowledge here, and we're updating it somehow. And your output is going to be WX, so this is your original output, plus ABX. And this is your updated information. Now, to make sure that this information starts out the same, they make BW, or they make B equal to 0. So that means that this here is just H is equal to WX on initialization. But since B is equal to 0, then you're not adding this new information. And you may think that if you look at the gradients, if you make it 0, all the way to 0, then they'll end up being the same. but they don't. If you have like dropout and stuff, then you add a little bit of randomness in there, and then they don't become the same. So after one update, these parameters will no longer be 0, and it'll start to add on to WX. So WX is always static, A and B are always changing, and you have this low rank matrix that you're using. And that's all LoRA is. It's literally just saying we're adding an A and B matrix here, and that's the weight we're going to update instead of using W. And if we say R is really small, 16 is a good value to choose, then all you're storing is R by D instead of a D by D matrix. And D is usually 2048 or 1024. So it's a significant decrease in memory, and you're doing this for each
normal
other.
distribution, that's just like HE. That's like a classic initialization.
Yeah, that's just normal initialization.
Yeah.
So that's all you're doing, and you may think, well, if it's low rank, we have less parameters we're optimizing, it'll do worse. It actually does the same or better sometimes. So you don't have any loss, and you're storing like 0.1% of the parameters when you're fine tuning. And if you do this in practice, it actually works. So yeah, that's all LoRA is doing. It's for every matrix here, you add two LoRA matrices, A and B, on there, and then it optimizes those instead. And the best part is, you can merge these. So whenever you're done optimizing these LoRA parameters, you don't even have to do extra computations. So we have H is equal to WX plus ABX. If I take out the X, so W plus AB, and then I say that we'll say N is equal to W plus AB, because this is a D by D matrix, and this is also D by D whenever you multiply them, then all you have is H is equal to NX. So you have this matrix here that doesn't store up any extra memory because you can combine them together, and it doesn't take up any extra computational cost after you're done training it. So literally, it's perfect. It's beautiful. But that's LoRA. It's pretty simple.
So LoRA is actually used a lot in Stable Diffusion. So like if you have because Stable Diffusion models are gigantic, right?
Well, it's used everywhere.
It's used
LLMs.
honestly, it's used everywhere, yeah. But I just know them the best from Stable Diffusion, so that's why I'm using that one as an example. But like, if you have a giant model, right, and you want to kind of alter the style of what it's outputting, because different Stable Diffusion models are going to have different styles when they output the images, right? So like if you generate image, all of them are going to have different styles, kind of like, especially if they're fine-tuned on like anime images or something. Yeah, don't judge me, okay? So like if you want to alter that style a little bit without having to fine-tune the entire model, which would, like as we talked about, would
destroy it.
Bad. You can just alter these LoRa weights, literally add them directly in, and it does exactly what you want them to do. So it's the nice way of doing.
It's smaller, and it does better, and it doesn't add any overhead. There's no reason not to use it. And when you're doing fine tuning, this is what you use. Any fine tuning with linear layers, you use this. But do we need to go through QLoRa?
We can literally just talk about why it's good.
Do QLoRa or
Why I got it.
All right.
You guys.
Yeah.
It's like 5 minutes anyway.
It's elite.
It's like
QLoRa?
It's literally, it will take like 5 minutes, 10 minutes.
Well, literally all you do with QLoRa is you take this matrix here, and you store it in 4-bit. So that's all you do. And they say, well, you have your weight matrix, and it turns out that your weights end up as a normal distribution. Wow, that's convenient. So if you kind of compute this normal distribution, the way I think about it is you can kind of split it up evenly, like this. And with quantization, you have to bucket this somehow. You have to take 32-bit precision, and you have to bucket it. And 4 bits, that's 16. 16? Yeah?
Yeah.
All right, so 16. So you take like infinite numbers, something to the 2 to the 32, so a massive amount of numbers, and then you put it into 16 buckets, and yeah, you have to do a good conversion. So what they do is they say the weights look normal, like a normal distribution whenever they're done training. So you can discretize it into, you can basically cut up the normal distribution, and that's your bucketing. So the weights would go here. These weights would be, like you look at the weights, you find this parameterized distribution, and you bucket it, you split it up, and then you store the values in there. And upon training, you reverse the 4-bit. So you have an inverse transformation, which is super lossy. So you're just storing W in 4-bit, but you transform those back into 16-bit, do the multiplication, and then you store them in 4-bit.
So your gradients are 16-bit.
Yeah, but they're only 4-bit because that's all the precision you have. So all you're doing is you're storing W in 4-bit, and then you're converting it to 16-bit whenever you need to do the multiplication.
The
smaller.
normal float thing, like it seems kind of dumb, but it actually works really well.
It is dumb and it works well. Yeah.
Like, because people tried doing it with standard 4-bit and it
didn't
was
work.
Terrible.
But this works well.
Trash.
Like
But
it's
this works.
stable.
Like,
but that's all you do.
You can train like a 70. What is it? You can train the.
You can train 70
mil
billion.
on
4-bit. Yeah.
on how many, like what size of GPU did they use in the paper?
I forget. Yeah, it was a large one. But
it's like huge models on like really small GPUs because you're storing 4-bit.
yeah, you're storing it in 4-bit and you're using LoRa, so it's a lot less parameters. It's it's
really
like 0.1 parameters or 0.1% or something like
There were a
that.
couple other things they did that were kind of dumb. So one thing they do is when you quantize, there's something called a quantization constant, and that's how you store your buckets.
And then they
So
quantize
they were
the
like, why don't we
quantization
quantize
constant.
this, and that also worked
Yeah,
for some reason.
the quantization constant is in 32-bit, and you quantize the quantization constant into 4-bit, and those have a quantization constant, but you only have one quantization constant, and it ends up being better.
Yeah, so the
It's-
quantization constant basically like tells you how to get back to where you
Yeah.
were. So
Yeah.
like
It's,
you,
it's
like
some
a
scale
reverse.
factor.
yeah, like when you basically are compacting all this stuff into not like a smaller space.
Yeah.
And then you're making it so it's like 4-bit instead of whatever the hell it is, like 32 floating point.
You need an
whatever.
inverse transformation, and that's what the
So you need
constant
the
is.
inverse transformation to go back up to what you had before. So they have this constant, and then but usually that's going to be 32 point. But it's going to be the same as the thing that you start from, you quantize
And
from,
they're
right?
like, oh, let's quantize this, and it works for some reason.
Yeah, and I also do something with paging.
Oh yeah, I forgot about the paging.
Oh yeah,
Oh, I remember
they
that. So what they did was, so if you have a small GPU, right, one thing that can happen is when you're trying to do your gradient calculations, you can run out of memory really easily when you try to backpropagate. So basically they did some stuff in CUDA where basically when it seems like the GPU is, and when your GPU gets too high of workload, like you don't have memory left, your performance degrades, right? So you don't want that. So what they do is when the memory gets too high, they basically automatically just take some of the weights that aren't being used, and they just shove it on the CPU. And then when the GPU frees up again, they put it back.
Yeah, which is
That's it.
another thing they do. But the main thing is you can store the original D by D weight matrix in 4-bit as opposed, and that's the only thing you
The
store in
normal
4-bit.
float is the big thing,
Yeah.
I think.
Normal float in 4 and storing the normal float, an efficient way to store the original weight matrix in 4-bit that actually works.
Yeah.
But that's QLoRa.
It actually gets really close to like full fine-tuned precision, like surprisingly close.
Yeah. Very.
Yeah.
Yeah.
Like it's
QLoRa.
pretty crazy. I remember when paper first came out, like I don't think anyone like believed this.
Nobody believed it.
Yeah, I was like, this is such cap. There's no way.
But it just works.
But
Yeah.
it works, and people have used it, and it works.
It always.
yeah,
it-
everyone uses it now.
Yeah.
It's really good.
Yeah.
But there we go. Tension, LoRa, QLoRa.
You guys had any